exciting talk is going to be about analyzing key derivation functions. Matteo and Sebastian are going to give the talk. The floor is yours.
Hi, thank you very much for the introduction. My name is Sebastian, and I'm here with Matteo today to talk to you about a very fundamental primitive, the key derivation function. But not any key derivation function, but key derivation functions that take as input multiple secrets to combine them into one single output secret. And we will discuss the lessons we've learned when analyzing real-world constructions of this primitive. But first, let's back off a bit and talk about what the key derivation function is. On the left, you see a very basic Diffie-Hellman key agreement protocol. You have some user which sends a shared G to the X to the server, which responds with a shared G to the Y, which they can then use to get some element that looks uniform within the group. However, it only looks uniform within the group and is not a uniform bit string. Also, protocols like to add some additional information into the derived key, like context binding to increase security. This is where key derivation functions come in. Over time, key derivation functions have converged on the following inputs. So they take a secret, the G to the XY that we just discussed, some label which handles additional information, and a length output which ensures that the output key has the correct length for the cryptographic application that wants to use the key later. Also, from extractor theory, there is a salt value that is input in the KDF, which job is to smoothen the entropy of the final key to ensure that it is uniform. However, when we looked at what constructions that are deployed actually do, we realized that basically none of them use the salt value as it is intended, but just put some fixed string in as the salt input. As a consequence, we've come up with a model to analyze these key derivation functions without relying on the salt value. So as you all know, with the quantum thread advancing, the Diffie-Hellman key agreement that I've just shown you really no longer does it. So in practice, you would probably have a protocol that is more like this, where in addition to the Diffie-Hellman key shares, you now also have some CAM key agreement. So now client and server have a G to the XY and also some shared secret lowercase k. Now the KDF already has all its inputs satisfied, and there's not really any place to put this additional key and this additional context that might come up as part of the CAM key exchange. So in practice, constructions have had to deal with this and have come up with solutions. I've brought with me here two examples for multi-input key derivation functions that are deployed in practice. And they kind of do well in exemplifying the two design paradigma that we've observed. The first is the MLS PSK KDF, which is used in MLS to combine the pre-shared secrets. It uses an iterative construction and loops over the input secrets, calling HKDF multiple times on each secret. In contrast, there's CAT KDF, and it was proposed by ETSI, which does not iterate over the secrets, but concatenates all the secrets and then using them as one big input to HKDF. On the topic of interfaces, we can also observe that they deal differently with the label input. MLS does not take a user-defined label input, but uses the empty string and fixes this to the string MLS derived PSK, while ETSI CAT KDF lets the user choose an arbitrary label. So this leads me to this discussion on labels and contexts. When we first started analyzing key derivation functions, and especially key derivation functions that combine multiple input secrets, we were quite confused by the notion of labels and contexts, and also the notion of an info field, which sometimes appears, which also somehow gets input into the KDF. So we have come up with the following logic. We say a multi-input key derivation function should have one single label that is somewhat associated with the final key. For this purpose, we can call it the real-world cryptography encryption key, or MAC key, or whatever. And in contrast to this one single label, we have multiple contexts. And to be precise, we have exactly one context per input key. So for our example, we would have two contexts, one for the Diffie-Hellman part and one for the CAM part, where the context consists of the transcript that can be observed, but also like public parameters, the CAM algorithm, or any other metadata that should be included in the protocol. And now to highlight why this is important, if you look at the etc KDF, again, as I've shown you before, you see that it does take this label input and then uses it as an input for HKDF. However, HKDF doesn't really expect a label input, but more of a context input. So the label is used as the salt input to HKDF, which can lead to a problem. If we look at how HKDF works, it first performs an extraction step with the salt, which is now the label. And if we look at how this extraction step is defined, it uses HMAC, which is a keyed primitive, where the key is the salt, which again is the label that is provided to the etc/KDF. And actually, the first step of HMAC hash is to append zeros to the end of the key, which is the salt, which is the label, until the desired length is reached. As such, it is very easy or trivial to generate labels that yield to the same output of HMAC hash. So you can have different labels that, when input into the multi-input KDF, result in the same key. Now, this can relatively easily be fixed by just fixing the label length. But we've also found constructions where the issues are bigger. Now I hand over to Matteo to tell you about his analysis of MFKDF.
Yeah, so as you've probably seen, multi-input KDFs are hard to get right. And even if no boxes were harmed in the production of these slides, I will try to talk to you about another attack that we discovered on this MFKDF construction proposed at Usenix 23 by Nair and Song. What they want here is to derive one key given multiple inputs. So we're clearly in the multi-input KDF settings. And so let's abstract away a lot of the details of MFKDF. Just look at this schematic diagram. We have several inputs, each with like different entropies. And so for instance, in this case, we have a password and some HOTP, TOTP factors with 40, 30, and 30 bits of entropy. What we would want to have at the end is a key with at least 100 bits of entropy. MFKDF does this, but not just this, also more. They also provide a threshold variant. So you can set up MFKDF with a 3 out of 4 threshold, and then you should still get at least the entropy that the set of the minimal set of 3 factors should provide you. So in this case, still 100 bits. How does MFKDF do this? Well, they start by sampling a random final key, and then they secret share it in n shares. So in this case, now I switch to 2 out of 3 shares just to make the things fit in a slide nicely. So now we have 3 shares, and if you haven't heard about Shamir secret sharing before, what this gives you is that you can pick any 2 of these shares and rederive the key. Okay, so any combination of the shares will give you back the key. But how do we factor this Shamir secret sharing implementation into the bigger picture of MFKDF? Well, we take our factors, we derive a key from each factor, and now we plug in the bottom part. So we take our final key, secret share it, and then we can encrypt each of those shares with a key from each factor. Okay, and now we have encrypted shares. We can put them in a public state and upload this public state somewhere in the cloud, so that when we want to rederive the key, all that we need to do is input our original factors, derive key from these factors, retrieve the state from the cloud, decrypt the shares, and rederive our key. Okay, so pretty neat, right? Are you convinced by this? Well, turns out that, I mean, probably I wouldn't be asking this question if everything went right. Well, let's look at decryption. So we would expect to get 60 bits of entropy out of this. But what if we took a guess for the password, and then we did trial decryption of a share? Now the output would either be something that looks like a share, Shamir secret sharing share, which is, by the way, not uniform in most cases, or something that looks like uniform randomness, or even a bottom if we were using authenticated encryption. And so what this means is that we can brute force factors separately. So for instance, we could brute force all the 2 to the 40 possible passwords and all 2 to the 30 possible HOTPs. And this would give us an entropy of 2 to the 40 plus 2 to the 30, which is much smaller than 2 to the 60. Okay, so clearly something here went wrong because like we get a security level much lower than what we would have expected. Now, I must tell you that this bug is a bug in the specification of MFKDF. There are actual reference implementation as other bugs that cancel this one out. So we don't have a practical proof of concept exploit. Like my paper with Matilda Backendal and Miro Haller actually finds a lot of other problems with this idea of deriving keys from authentication factors. So we have a lot of attacks in our papers. If you find it interesting, check it out. To the defense of the MFKDF author, though, we must say that this primitive that they were trying to implement of having a threshold NKDF, so multi-input KDF, is actually something that is not well defined in the literature. They were trying to build something new and something for which we don't have a model yet. And therefore, they didn't even have a security notion to target. And so what is a secure NKDF? Well, to answer this question, I will give the floor back to Sebastian.
Thank you very much, Matteo. Yes, indeed, we ask ourselves, how does a secure multi-input key derivation function look like? You see here the syntax that I've discussed before. So we have multiple input secrets, up to n in fact, and each input secret has its associated context. Then there is a label value and a length value. For simplicity, I will, on the following slides, only talk about KDFs that take 2 inputs, but everything I say basically extends to the n input case. So in our security game, we basically want that with these inputs, we get an output that looks random. And now we want that it looks random, not only if all the input secrets are secret, but we allow an adversary to compromise actually some input secrets. In this example, the second input secret, the associated context, the label, and the length are all adversarially controlled. So there's only one good input secret left. And for this, we want that the output of the KDF still looks random. Actually, KDFs are deployed in a number of places. There's stuff like extendable and non-extendable output functions. There's keys that may only be used once. So it's a bit complicated, and we have different predicates that you can use to deal with this in a formal analysis. But there's also 2 major settings that I want to highlight here, in which KDFs can be analyzed. So the first one is the hybrid setting, as I've discussed in the very beginning, where you have some established primitive with a proven implementation and something new that is used in a hybrid manner. Now, with such a system, you would expect that either like the quantum computer arrives and all your Diffie-Hellman secrets are broken, or that there's some issue in the implementation or the math of the newer schemes, and all the new stuff gets broken. But importantly, it's always the same input that is either good or bad, and there's no mixing in between. This is what we call the hybrid setting. There's also the more general setting, where you do not fix a single input to be either good or bad, but the adversary can adaptively choose which input secret he wants to learn or even control himself. Note that for security, obviously, we always need that at least one of the input secrets remains unknown to the adversary. And in these 2 different security settings, you get different security bounds. So we took this model and actually applied it to a few constructions that we have found in the wild. One is the pre-shared key combiner used by MLS that I've shown before. And we can actually show that the MLS combiner is a good combiner for pre-shared key keys in the way that it is used at the moment. We've also looked at cat_kdf as it is proposed by ETSI and have found the issue with the label that I've shown earlier. However, it is important to point out that cat_kdf was never really meant to be a general purpose multi-input key derivation function, but it's more tailor-made for the case of a hybrid key agreement. However, other agencies like the BSI reference these standards, and the interface kind of gives you a more general construction than what is advertised. And with the restricted label set, you can actually use the ETSI cat_kdf outside the scope that they advertise and have it as a secure multi-input key derivation function. Lastly, we looked at Signal and the way they use a KDF in their X3H key agreement, and also found that this is a good use of a multi-input key derivation function. Throughout our analysis, we have seen that the way these multi-input key derivation functions are built follows some kind of a generic blueprint. Analogous to the extract and expand paradigm that you have in HKDF, for multi-input key derivation functions, you have more of a combine and then expand paradigm. And importantly, the combine step only takes the secrets and associated contexts, while the expand step takes the label and the length on some pseudo-random key that is output by the combine step to give you your final key. And this modularity actually allows you to have a look at both pieces individually. And for the combine step, you actually need a simpler primitive, which we term a combiner in KDF, where you do not need to worry about either labels or the output length. And for the expand step, you can just use a PRF with variable output lengths. This primitive is readily available. You can, for example, use HKDF expand or shake for this. So this leads me to my lessons learned. To recap, we have seen that this actually has pitfalls if you try to design a multi-input key derivation functions. Now you can use formal analysis to actually validate your constructions and gain trust into the constructions that you have deployed. Using this model, we've been able to give positive results on Signal and MLS. This talk was based on 2 papers. The MFKDF part was published at Usenix last year, was called Multiple Factors Knocked Down Flat. Check it out if you want to learn more about MFKDF. If you want to learn more about key derivation functions with multiple inputs, have a look at Eurocrypt this year, where our paper will appear. It's not yet on ePrint, but will be very soon. This concludes my talk, and we're now very happy to take any questions.
Great, thank you.
Thanks for the talk. One question about cat_kdf. So if I'm not mistaken, it runs the extract function on the concatenation of secrets.
Yes.
And as far as I'm aware, HKDF wasn't proven secure in that sort of hybrid model where you have a concatenation of secrets, one which can be sort of maliciously chosen. Do you have analysis as well that sort of validates that use of HKDF extract?
So we've analyzed ETSI cat_kdf and shown that you can have malicious inputs. Let's discuss HKDF offline.
Thanks.